Hello, you are welcome to this video. My name is Dr. Kingsley. Okay, earlier we did chemical kinetics, okay, and we saw different orders of reaction. I just want to make this video to show you the summary of all the different orders of reaction, the features of each order of reaction, so that you'll be able to know, okay, how to differentiate zero order reaction from first order from, okay, second order reaction. Now, if you look at the board here, you'll find out that we have here features. Here is zero order reaction, here is first order reaction, and here is a second order reaction. Now we will begin with what? Differential rate law. What is the differential rate law for zero order reaction? For zero order reaction, rate is equals to constant. That is to say that the rate of zero order reaction does not depend on concentration of the reactant. Now, the differential rate law for first order reaction, okay, is that rate is equals to rate constant multiplied by the concentration of the reactant. That is to say that for first order reaction, the rate is directly proportional to the concentration of the reactant, directly proportional. Now for second order reaction, the rate is equals to the rate constant multiplied by the concentration of the reactant raised to the second power. So raised to the second power means that it is a quadratic. Okay. Now that is for the differential rate law for this what order of reactions. Then here we have integral rate law. The integral rate law for zero order reaction is that final concentration is the initial concentration minus rate constant multiplied by what? Time. Okay. While that of first order reaction, you will have lane of initial concentration, lane of final concentration is equals to lane of initial concentration minus the rate constant multiplied by time. That is for first order reaction. Then for second order reaction, 1 over the final concentration will be equals to 1 over the initial concentration plus the rate constant multiplied by time. So these are the what? The integrated what? Rate law for zero, first and second order reaction. Then also we have straight line graph. If we plot a straight line graph, if we want to get what the graph of these orders of reaction, we are plotting what? The concentration, that is the final concentration against time. If we plot final concentration against time, okay, and this is what? A straight line graph. It will show that what? That the reaction is zero order reaction. So one way to get to know whether a reaction is zero order reaction or not, you can, okay, measure the concentration at different time when the reaction is ongoing. So when you measure the different concentration at different time interval and you make a plot of what? The concentration against the time, if you have a straight line graph, then that what? Reaction is what? Zero order reaction. Now for first order reaction, it is lane of concentration, that is the final concentration, the lane of final concentration versus time, that will give you a straight line graph. That means you measure the concentrations at different time as the reaction proceeds. Then you take the lane of the initial, you take the lane of the final concentration at different intervals of time and you plot, okay, the lane against what? Time. If it gives you a straight line graph, then the reaction is what? First order reaction. Now for second order reaction, it is the reciprocal of the what? Final concentration versus time that is going to give us a straight line graph. Now slope. Now if we plot this graph, that is if we plot a graph of final concentration against time, okay, for for zero order reaction, the slope will be what? Negative. What are we doing? We are plotting final concentration, final concentration rather, pardon me, final concentration. You plot final concentration against what? Against time. The slope will be what? Will be negative k. That is minus rate constant. Now for first order reaction, if we plot length of the final concentration against time, okay, the slope of that graph is going to be what? Negative k. That is negative of the what? Rate constant. However, if we come to the second order reaction, you plot, okay, 1 over final concentration against what? Time. You see that the slope of the reaction will be what? Will be positive. So that is how you can use what? The slope of reactions to tell whether it's zero order, first order, or second order. Then half-life. Half-life is another way to, okay, know the order of reactions. If you are working with what? Zero order reaction, we will see that what? The half-life of zero order reaction is concentration, that is initial concentration, divided by 2k. K is the rate constant. Why for first order reaction? The half-life of first order reaction is 0.693 divided by what? By the rate constant. Then for second order reaction, the half-life is what? 1 over rate constant, okay, multiplied by the original or initial concentration. What does this tell us? This tells us that what? The half-life of zero order reaction depends linearly on the what? On the initial concentration. Also, if we go to first order reaction, we see that what? The half-life of what? First order reaction is independent of what? Initial concentration. Then we go to second order reaction, we see that what? The half-life of a second order reaction is inversely proportional, because we are having the inverse. Inversely proportional to what? To the, okay, initial concentration. All the half-life depends on the rate constant, but only the first order reaction will the half-life not be dependent on the initial concentration. Now, if we plot the rate of reaction versus concentration, you see that what? The graph will be horizontal line for zero order reaction. Why? Because the rate of zero order reaction does not depend on concentration. It is constant. That is why we are having what? Horizontal graph. Then the rate of a first order reaction against what? Concentration will be a straight line graph that is starting from the origin. Remember, the rate for first order reaction is directly proportional to what? To the, okay, concentration of the reactant. There is no intercept, so it will be a straight line graph. Now to the second order reaction. If we plot rate versus concentration for second order reaction, you see that rate is directly proportional to the square of the what? Of the concentration. That means concentration raised to the second power. So since this is quadratic, we will expect that what? The rate versus concentration will give us upward what? Curve. That is what? That is a quadratic. Okay. Then finally, what are the typical examples for zero order, first order, and second order reaction? Now, photochemical reactions are zero order reaction. Enzyme catalyzed reactions at saturation, enzyme catalyzed reactions at saturation, they are zero order reaction. Then first order reaction, example is what? Radioactive decay. We also have what? Hydrolysis of esters, acid hydrolysis of esters. Even decomposition of ozone is also first order reaction. Then second order reaction is on gas phase what? Reactions. Now if you follow this table very well, you will be able to use it to differentiate what? the zero order, first order, and second order reactions, as well as it will help you to remember each of these words, these equations, so that you can easily use them in calculations. If you have enjoyed this class, subscribe now, share my video, and like. Thank you very much.